Hello and welcome to part one of this week's lecture. In this lecture, we are going to look at different fluids in motion and how we can characterize these fluids in different flow regimes. We will look at viscosity in more detail and what are the implications of viscosity in fluid flow. And finally, we will develop some formulations for velocity profile for laminar flow. So just to remind you of the big picture we have been discussing so far, we are discussing fluid mechanics, and we can divide fluid mechanics into fluid statics, that is the study of fluids at rest, and we discussed in lecture 2. In this lecture, we are going to look at fluid dynamics, that is the study of fluids in motion, and particularly we will look at hydrodynamics, that is the study of liquids in motion. Okay. So what is a flow, for example? So flow is the motion of fluid, a fluid moving from one point to another point. And normally we experience this in our daily life. When you open a faucet, the fluid comes out of the faucet and moves from the tap end to the sink. And this motion of the fluid is caused by the pressure difference. So all the flows are always associated with a pressure difference. It means that the fluid flow from a higher pressure to a low pressure. And here I have given you an example here. So here you have two columns filled with water. So here you have a column that is taller than the second column, and you can see that if I open the valve, the fluid will flow from here to the second, from the first column to the second column. Okay, because there is a high pressure here compared to here, and then you will have a flow. But once the level in these two columns become equal, there is no flow anymore because there is no pressure gradient. Similarly, for the case of gases, you have two tanks connected, let's say, through a valve. And if I open this valve, the tank one, let's say, is at high pressure, and the second tank is at low pressure. So the gas will move from a high pressure tank to the low pressure tank. Okay. So we established that the flow, that is the motion of fluid, and is caused by the pressure gradient, and this motion caused a change. So a change in what? So the change in, obviously, the element of fluid is moving from one place to another place here, for example. So there is the relocation of this fluid element, but also a change in velocity, pressure, density, or some other property of this fluid. So for example, here if you look at this simulation, here you have blue particles that are flowing at much lower velocity, and then these particles go through a constriction, and that increases its viscosity in the form of red particles here. Okay, and it is clear demonstration that the velocity is changing from here to this part here. Okay, and that is what we call a fluid in motion. There can be other types of fluids or flow descriptions. For example, we can have a change in property with respect to location. So if we consider a distance or change in property with respect to location, we can have a uniform flow. The uniform flow is a flow in which the properties or the flow conditions, that is velocity, temperature, for example, or density, remains constant from section to section. It means that the property at this point will be equal to property at this point here in x direction over a length, let's say x. Yeah, and that is shown here that the velocity is not changing with respect to distance, and that is why your velocity is constant. Okay, and a common example is, for example, here you have constant discharge through a constant diameter pipe. Okay, then we can have another situation that what we call is a non-uniform flow, in which the flow conditions uh, are changing with the section to section. So for example, your velocity at this point will be different to your velocity at this point. Okay, that is, let's say d2, and that is point d1. So you have a change in velocity in over this distance. And mathematically we can write it as the velocity with respect to partial x, that is the distance of change, is not zero, and that means that your velocity is variable. Okay, and a common example of it is, for example, if you have a constant discharge through a variable diameter pipe, and that is the situation here, for example, that you have a certain diameter and you have a certain velocity, but as the diameter is changing, your velocity is changing as well because of the conservation of mass. Okay, that is why we call this situation here a non-uniform flow situation. Then you can also have a change of properties with respect to time, for example, and you will see it very often. So one is when the flow properties remain constant with respect to time, we call it steady state flow or steady flow. And one example is that, for example, here you have velocity 1 at t1, and then you have velocity 2 at t2. So if these two velocities are equal at these two different times, it means that the velocity didn't change, and as such the flow is a steady state flow. And mathematically we can write it as partial v over partial t is equal to 0, and again because the velocity is not changing, so your velocity is constant. And a common example of this is a constant discharge through a pipe, just like the previous example. And then we can have another situation or another type of flow that is called unsteady state flow, in which the flow conditions change with respect to time. And for example, here, as you can see that the velocity is changing with time. So velocity at point 1 and t1 will be not equal to velocity at time 2. Okay. And this is what we call unsteady state flow. And a common example is that a variable discharge through a pipe. Okay, so as the flow will have, for example, you have this pipe and you have velocity here and you have velocity here. So these two velocities will not be equal, and that cause unsteady state flow. And we can also have flows in different directions. So for example, we can have 1, 2, or 3 dimensional flow, and here this word dimension is not related with units and dimension. Here what we mean is dimensions as in 3 different directions. So we have, let's say, x direction, we have y direction, and we have z direction. Okay, like a 3D model of your room or any object, we have always 3 dimensions. So we can have, for example, a unidirectional flow or one-dimensional flow if the velocity is changing in only one direction. For example, flow through a pipe, we can always approximate it that the velocity is changing only in x direction. Okay, so we can ignore the y and z components of this velocity. Okay. While we can have situations where we are looking at two-dimensional velocity, for example, here we are looking at aerodynamics of this car here. So we have one component of velocity that is in x direction, and then we have another component, as you can see here, we have a component that is actually changing with respect to y direction. Okay, so we have two components of velocity. It means that the v or u depend on x component and y component. Okay, and then we can have very complex situations, and unfortunately these situations are more realistic, but they are very complex in terms of solving them. So we can have a situation where the velocity is changing in all these 3 components. So you have velocity that is going in this direction, then you have velocity that is changing in this direction and in the z direction as well. Okay, so such situation is what we call 3-dimensional flow. And here the example of a stirred tank, where you can see the velocity vectors are going all over the place. Okay, then we can also have other types of flow called internal versus external flow. So we can have internal flow if the flow is inside a pipe, for example, that is the example here. And we can have external flow if the flow is, for example, is in open channel, like for example a river or a canal, or a flow is around an impeller, for example, impeller of a boat or propeller of a plane, for example. So these flows will be called external flows, okay? And we will discuss these in much more detail in the coming lecture. So here I'm just defining these flows, that what actually they mean, okay? So for this unit, because it is a fundamental introductory unit, so we will be mostly looking at one-dimensional flows. It means your life is quite simple in terms of solving equations. We will be looking at internal flows. It means you will have boundary conditions or fluid that is surrounded by a wall or a boundary. Then you will have steady state flows. It means that we will mostly look at systems where the velocity is not changing in time. Okay, so all these things make the situation much more simple, okay, in terms of solving it mathematically. So fluid dynamics is a very visual subject. It means that you can actually see the changes as they happen. And a set of techniques that we can use to visualize a flow is called flow visualization. And these flow visualizations can be experimental or can be numerical. And for example, here you can see a flow visualization, a numerical CFD simulation, computational fluid dynamics simulation, where actually you are looking at the air drag that is shown by these lines, that is for this cyclist or this helmet, for example. Okay. So these flow visualization, or these lines that we use to visualize the flow, we can have different types of these lines. So we have streamlines that is shown here. We can have stream tubes, and we can have streak lines. So let's have a look at what these different lines mean in terms of visualizing a fluid. So to picture the motion of a fluid, we can start by examining the motion of a single fluid particle over time, or a collection of particles at one instance. And this particle, for example, here we have one particle in the fluid, and each of this particle or this point have a velocity vector that is tangential to this point, and then we have an acceleration vector that is normal to this point. Okay, so each point will have these two vectors, and if we collect this one point, and then the fluid is moving, for example, like that, and if we collect these points, we can get and connect these points, we get a streamline. Okay, and as you can see here, so each of these points will have a tangential vector, and if we combine these points, we get a streamline. Okay, so it means that the fluid actually is flowing in between these streamlines, and when this point is changing, it means that the fluid is changing its direction. Okay, so from here to here, like that. Okay, so these lines, or this boundary actually entrap the fluid particles. So a streamline is a tangential to the velocity vector of different particles. And as I said, that this is just an imaginary line that you use to visualize how the fluid is flowing for numerical analysis. And if we combine all these streamlines in the form of a tube, so for example, here you have one streamline, second streamline, third streamline, and we make this boundary around it, or a tube around it, so we call it a stream tube. So just to show you how these streamlines look like, for example, here you can see that this, for example, smoke is used as a representation of this streamlines in reality. So for example, you have a car, and different jets of smoke are hitting this car, and then showing you how these streamlines will look like in a simulation, for example, here. And these lines of the smoke, that is what we call streak lines. Okay, so streak lines are actually streamlines that we use in an actual experiment. So streamlines are for numerical calculations when we use a system or a software, for example, computational fluid dynamics, and we generate these imaginary lines to represent the fluid, the motion of the fluid. But if we use an actual experiment, for example, as I showed you in this previous slide here, we call these lines streak lines, okay? And here there is another example. So here, for example, you have a fluid that is moving in this direction, and then you have this, for example, a column as a resistance. So this fluid is a mixture of aluminium powder and glycerin, and you can see that the lines that you can see is the lines formed by aluminium powder as it flows through this system, okay? So here you have, you can say all the lines are straight, that show you that you have a uniform region. It means that the velocity is not changing. And then you have this region where you have a kind of a mixing, and that's what we call eddies. And it means due to this resistance of this column, from uniform flow you get a non-uniform flow where the velocity is changing in all directions, for example here. And just one thing that I forgot to say about streamlines, that the distance between the two streamlines represent the velocity of the system. Okay, so for example, if you are looking at this stream tube here, and so the fluid is flowing between these streamlines here, okay, and so when the fluid is entering, the two lines are further apart. It means that you have a low moving fluid, and as you move and the fluid is changing direction due to a restriction or a constriction, you have these streamlines coming together, and it shows that the velocity here is much larger. Let's say velocity f, velocity vi. So this shows you that the velocity at final velocity is actually larger than the velocity in the beginning. Okay, so the distance between the two streamlines can tell you the value or the indication of velocity. And that is as I was showing you here. So here you have streamlines, but here you can see that the streamlines kind of stretching out and becoming much closer. It means that you have an increase in velocity because of this resistance here. Okay. And another example of streamline or instantaneous streamline is, and here in this example we use CFD. Let me try to play it. So here if we play it, you can see that, so here there is a flow and you have very nice streamlines here, uniform streamlines, and then there is the object, and that is like a resistance column, and then you have, let me stop it here. So when these uniform streamlines where you have a constant velocity hits this object, you have what we called vortex formation. Okay, so because of this streamlines hitting this object, you have a change in velocity, and as such you have a vortex formation. And after a certain time of this vortex formation, what we call vortex shedding, it means that the vortex is actually now, you don't have a vortex, but you have how the velocity is changing as the fluid is moving through this region. Okay, so let me play it again. So here you have much uniform region, but after this one it's hit, you can see that you have a change in the velocity profile or the velocity or the streamlines. And as you can see here that due to the change in velocity, the distance between the streamlines is much smaller here compared to the distance in the streamline here. Okay, so that gives you an indication that just by looking at it, that that the velocity is being changed as you move around this object. Okay, lecture, and in the next lecture we will look at different flow regimes. Okay, thank you for your time.